colloquium speaker, David Soderblom, at Space Telescope, and recently also with a joint appointment at Johns Hopkins. David grew up in California, spent his undergraduate years in the 60s at Berkeley. Those were interesting times in the 60s. And then moved on to Santa Cruz. And that was in the 80s. And 70s. And then at the beginning of the 80s, he spent a few years here in Cambridge. Oh, he was hitting all the high points. And after that, went to Baltimore, where he's been ever since. In 1990, David and I quite independently submitted proposals to NASA's SETI program to help them out with their target selection for the targeted survey.
Which they didn't know they needed, right?
Well, that's right. And so that's how we ended up working together. And it was my first exposure to NASA, so I had some trouble figuring out what TLAs were. Three-letter acronyms, right? And David and I invented a new TLA, the WTE. Can anybody guess what the WTE was? No, the wine tasting element. And we organized wine tastings at all of the science team meetings, and it really livened up the science team meetings. The reason for mentioning that is that David has inspired me to do a wine tasting in this room tomorrow at 4:30, and you're all invited if you'd like to join us. And since the varietal Zinfandel is in David's pass, we're going to feature some Zins. Well, anyway, I'm going to let David tell you about the challenging problem of determining stellar ages.
So, thanks very much. That's about the best introduction I ever had, and I'm about to get the best send-off I've ever had tomorrow. So what a deal. And it's a real treat to be here and to see lots of you who I've known for a long time. And I got to say, when I start, this is the very first time I've ever spoken in a place where I can actually preach to the choir. And you guys up there, mind yourselves, don't make me come up there. Oh. We're going to talk about ages, and why would you care about the ages of stars? Why is it so darn hard? Some of the different problems of age, there's more than one problem. And then go into some specifics about what are some ways of thinking about age, of going about the problem of estimating ages, what are some different quality levels, what are some of the techniques. I will not dwell very much on young stars. I'll emphasize the older stars mostly. There was a review that's now in press in the latest Protostars and Planets about pre-main sequence and young stars. And then I'll go into the problem of how do we go from boutique, which is to say doing things ones or twos at a time, to retail, tens and hundreds, to wholesale, the thousands and tens of thousands, to the industrial level where you want to get if you're going to do studies of our galaxy and things like that. And then finally a summary of pros and cons and some conclusions. So why do you care? Time is of the essence in stellar evolution. We all know the Vogt-Russell theorem that the physical state of a star is a function of its mass, composition, and age. And of course, in reality, you have to throw in rotation, some things about companionship maybe, and the details of the composition. But mass, composition, and age are the big guys. But is that really what's going on? If I think about it, time is not a direct agent of change in the star. It's more like a medium in which the star exists and other things happen. It's not so much different than your body. Your body doesn't age because of the passing of time. It's because of things going on in your cells that happen in the context of things happening over and over in time. And as a result, it's really hard to tell. I can't tell how old you are except in very general ways, right? And the only reason you know how old you are is somebody gave you a piece of paper once that said so. And you have to believe that. You were there, but you don't remember. But one of these days, we're going to hear about and all the work that's going on, signs of a life on a planet around another star. And whether you believe for a moment what you hear about it, the very first question you're going to ask, I tell you, is how old is that star? Because you want to place that detection in the context of evolution. It's an essential question of that discovery. And how are we going to do that? In that case, that's one of the particular problems. The star of interest is going to be nearby. It's going to be off by itself in the field, not part of a cluster, and it'll probably be fairly old. And how are we going to be able to say something about that one particular star? So, what information can we use to estimate the age of a low-mass star? going to have to apologize to Bob back there for trying to upstage him here. Anyway, I'm going to dwell on low mass stars, ones that are convective and from their birth through the main sequence lifetime. How can we use it, and how precisely and accurately can we determine ages, and how does that depend on mass and age itself, and how can we do better? And methods that work for individual stars, not just groups. So some of the problems I say looking for ages are things related to planet formation and the evolution of protoplanetary disks around young stars. You're talking about age scales of the order of 10 million years, and pre-main sequence stars, small groups of stars, and in some cases single field stars. Another problem is the dynamical evolution of gas giant planets around late type stars. And we don't really know those timescales. We think maybe we know them, but we haven't established them. And there you're talking about anywhere from young to old main sequence stars and probably single field stars. Something of personal interest is creating a bona fide comparison sample for the sun. If you're going to understand the potential for solar behavior, the way to do it is to go out and look at some thousands of stars out there in the sky and not wait for the sun to do something in your face. And so if you'd like to understand the sun, you want to create a solar cohort. And the only reasonable way to do that is to know something about mass and age for those individual stars. Talking about using the properties of the stars, such as activity or rotation themselves, is big into question. You're doing circular reasoning. You'd like to understand the evolutionary structure and star formation history of our galaxy. And again, I would say the right way to do that is to get ages, reliable ages for individual low mass or evolved stars to span the full age of the galaxy and to sample all of its components. And for example, when you're studying the star formation history and disk heating, those are all interconnected. It's a little hard to pull out the disk heating problem from the star formation history itself. And this is the case where you want to go from wholesale to industrial. So notice that some of these problems call for wanting to get an age for that star over there. And you're limited in what information you might be able to pull out about that star. Other ones call for doing ensembles of stars or large numbers of stars where you don't necessarily have to get a winning answer for each star, but you've got to get statistically reliable results. So ages of field stars. I want to dwell on the field stars. I want to tell you something you probably didn't know. So you may never have heard of the Reverend Ebenezer Field. He was... He's actually the guy after whom field stars are named, believe it or not. And he was known as a rather dyspeptic, disagreeable sort. And in fact, he was so disagreeable that he became the role model for Scrooge. And I have to ask, well, anyway, judge for yourself. Quality levels. There's only one fundamental age in all of astrophysics. I don't mean just stellar physics, I mean all of astrophysics. There's a limit because of the age of the universe from WMAP, I'll give you that. Other than that, there's just the sun. I'll mention this in a minute. There are some what I call semi-fundamental ages where you really understand the physics going on, but you have to make some assumptions about quantities in order to come up with an age. So two of these are decay of radioactive elements, and another is kinematic effects, traceback for young groups of stars. Then you get into the sort of the vast middle of things with model-dependent ages where you can measure quantities and you can predict those quantities through calculations that depend on stellar models. So you're talking about asteroseismology, stellar isochrones, and the lithium depletion boundary for clusters. There's some empirical methods where you think you have a physical scenario, but it isn't well understood, and you have an empirical age relationship, and you can establish and hope to calibrate that relationship against clusters. And then finally, there's some statistical things which are largely useless that I will only mention. So the perfect age indicator would be something you can actually measure in single stars, and you can always measure it, I will emphasize, because this will come up later. It is sensitive to age and not other things. It's a high contrast signal, so its variation with age is fairly large. You can calibrate it and you can come up with quantifiable errors. And I would add to that you understand the underlying physics, or at least have a rationale for it, and you can establish the calibration involving a minimum of assumptions. In truth, what we'd settle for is sometimes just setting limits to the age, at least classifying things properly by age, getting the age order right, sorting stars, and then finally, ideally quantifying ages. So there's one fundamental age, and that, of course, is for the sun. It's an easy-to-remember number, 4,567 million years, with an error bar of actually less than 1 million years statistically and about 5 million years systematic. And the systematics have to do with the sequence of events in the early solar system. This is one of the most exquisite measurements in all of astrophysics, and that's because it's not astrophysics, it's really geophysics. This is why it's so hard to do the sun, do other stars, because after all, they do not give us meteoritic material with which to work. It's fun to go back and read. I get to quote Rutherford here. There's actually some papers before him where they talk about doing radioactive age dating back in the 1920s. But it was so interesting to see the concepts they had of the formation of the solar system at the time. And it's kind of charming to read the paper itself because the whole way of writing a paper at the time was so radically different. It's like a conversational letter to a friend kind of a thing. So in the semi-fundamental, we have nucleocosmochronology, a real mouthful. It means talking about radionuclide decay. And they're pretty fundamental. You understand the physics very well. And it's a very simple process. So the nuclei in question are thorium-232, which has a half-life of about 14 billion years, and uranium-238 at 4.5 billion years. So those work really well for galactic purposes. But you have to make an assumption about the starting abundance, and this is where you get into trouble. And you generally do this based on other R-process abundances. So this gives us an opportunity to get ages for some very old stars from the early history of the galaxy, and these stars are very faint, and getting the spectra you need is not real easy. So here's a case study of this star done by Sneed et al. A few years ago. It has an FE/H of about -3. And did a very comprehensive look at the heavy elements, and in particular they measured this thorium feature at 4019, and you can see it buried in there. You cannot do this in POP1 stars and stars of the disk because the other lines in there that are normally there are just way too strong. There's no way you can pick out this weak thorium feature. So they got ages by comparing the thorium strength to other lines from europium, iridium, lead, and uranium, and they come up with ages that span a full factor of 2. And the average is about 14 plus or minus 3 billion years. However, I note that 30 years earlier, Fowler and Hoyle got the same answer, basically trying the same thing with solar system material. So it didn't seem like much of an improvement. And the ages range all over the place. There was another study more recently where they looked at 77 stars, and they were able to actually measure thorium in 17 of those. There's a huge scatter in thorium to europium, so that was suggestive the R process is not universal. That's interesting in itself. But the ages they get range anywhere from 0 to 23, and I emphasize 0 to be polite because technically some of them were minus, you know. And I don't mean to dismiss these guys. This is tough work to do. This is just emphasizing how tough it is. And you get a 9 billion year error in your age from what is a fairly typical 2/10 Dex error in the thorium to europium ratio. So it shows you what the nature of the problem is. It ought to work, and it just doesn't. There's kinematic traceback using dynamical ages, and the point here is that over time, stars in the galaxy get distributed in velocity. There's disk heating and interactions with massive objects. We don't not yet know precisely what these massive objects are, giant molecular clouds, massive black holes, and so on, but the time scale is the order of a galactic rotation period, or a couple 100 million years. So if you confine yourself to young groups, they have not yet been messed around with enough in their velocities, so you have the hope of tracing them back kinematically. And you can measure the expansion rate of a group. You can try to back them down to the smallest volume, or you can look at when several groups were closest together. These tend to give different ages. This all depends on the quality of the kinematic data, and you really need good distances, not just proper motions. You need to know the galactic potential, so there's some model dependence. But it is independent of other methods. You do nothing spectroscopic here. You just are doing a geometric method. So that's a nice thing. Only works for groups. The trouble is that it's been applied, for example, to young nearby groups and to SCO send back in time to their birth regions. Those are the gray boxes. You use kinematics and the galactic potential. It's been well shown that you need radial velocities and parallaxes. Proper motions alone don't do it. There's too much uncertainty. And the problem is that the exact results you get for any group of stars, that the membership is small enough in some of these young kinematic groups that including or not a particular star can radically change the results. So there's been a lot of criticism of the usefulness of this, and you can get results that are different by factors of 2. I want to talk for just a minute, even though this has to do with very young stars, about the lithium depletion boundary, because it does give us, it leads me to one of the few positive things I have to tell you today. It's relatively new. It was first suggested as a way to tell very low mass stars from brown dwarfs. Both of those kinds of objects are fully convective, but the brown dwarfs don't ever reach core ignition temperature. And because the stars are fully convective, that lithium that's there gets destroyed very quickly down in the core of the star. So the effect was first seen in the Pleiades. The stars are close. That was Bosri et al. And they got an age of about 125 million years. And at the time, the age of the Pleiades was thought to be about 80 million years from the main sequence turnoff, from the massive stars. There's now lithium depletion boundaries for 9 clusters. And they systematically give you ages about 1.5 times the main sequence turnoff age if you do not include core convection, the older models. Now the nice thing is that the physics of the lithium depletion boundary is very simple. The surfaces of things like these low mass stars are complicated as can be, but the interiors are very simple. They're fully convective stars, and it's very easy to model what's going on. So they should be very reliable. So the good news here is that the lithium depletion boundary ages agree with the main sequence turnoff models if you include core convection in those upper main sequence stars, the ones around 1.5 solar masses or 2 solar masses that are turning off the main sequence in the younger clusters. And that presence of core convection has now been shown with seismology from Kepler. So there's a nice closing of the picture that the age scale for young clusters is now, I would say, well established and reliable. You've got 2 completely independent physical methods. Lithium depletion boundary, main sequence turnoff, very different physics, very different stars, and they give you the same age. So that's nice. So this is an example. The nice thing about doing this is that you don't really have to understand the abundances of the lithium in the stars. All you have to do is detect the lithium, because either it's there or it's not. And so, for example, on the right you can see in NGC 2547, one of these clusters, the upper limits the lithium starred in at about 3,700 degrees and down, and that allows you to determine the age to about 15% at 35 million years. So, model-dependent ages, isochrone placement. So this is something we've all done at some point in our lives, probably in grad school, at least. And you need the temperature and the magnitude or luminosity, and you need to know the abundance and some uncertainties, and you place the star on calculated evolutionary tracks. Now, this is a very different thing than fitting an isochrone to a cluster, because in the cluster you don't just have more stars, but you have a distribution of stars. You've got the whole shape, range of masses to define the real physical state of that cluster. And it's not easy necessarily fitting the main sequence turnoff in a cluster. Nevertheless, you do have that whole shape business to fit, not just the location of a single star. So this is very, very much more difficult. And isochrones are not invertible, and their distribution in the HR diagram is not uniform. So the results in error can be biased. And this is a classic case where you really want to apply Bayesian analysis. The ice, I guess. Maybe they're cooling our drinks for later. So Bayesian analysis helps you take account, of course, of the biases built into the models in the first place and give you more reliable results. So this picture shows an example of how you can have a given point in the HR diagram and have 3, this is not even taking account of abundances, just 3 completely different ages all go exactly dead through that point, even before you account for the error bars, with 3 different ages. That's because that's just the way things are. So, Jørgensen and Lindeman in 2005 did a synthetic study. And so what they did was the following. They took a whole bunch of stars, where they took them with known locations in the HR diagram, and then they applied reasonable estimates of error to those, and then applied the process of determining ages given their new locations with the errors to see how well they could back out the original age. And they used several methods, and they found the Bayesian was consistently the most accurate and had the smallest error. But even so, the errors were about 0.2 of a dex. That's about 50%. That's not all that heartwarming. Their sample was relatively massive and old. So I show here where the location of the sun is. That's below all their stars. So everything starts at about 1.1 solar masses and goes up. And the big points here are the ones where they have the best errors. That's where the error is below 20%, and then the rest of them have errors of around 50%. So you actually get quite a ways off the main sequence before you even get the errors down to the 20% level from isochrone fitting. However, as I mentioned, you can do clusters much better. They get very nice statistical errors. Fitting models to the main sequence turn off in clusters because you have the multiple stars to fit to. Metals matter hugely. So this is an HR diagram around the solar position. And if you blow up right around the sun, you can see plotted points with error bars for our knowledge of stars that are very much like the sun. I mentioned 16 Sig A and B at lunch. And there's the sun itself, and you can see how hard it is to place even stars that are pretty well behaved and well characterized in an HR diagram. So the green lines are for solar abundance, and the red lines are about 50% above solar, the Hyades abundance. And take a look at those error bars. We can reduce them in the vertical direction and luminosity from improved parallax from Gaia. There's some residual uncertainty from bolometric corrections, but it's still really tough to do the temperatures better. This remains a very fundamental problem, that the temperature scale is good to maybe 50 degrees absolute, and there has not been a good resolution of how to do better. And 50 degrees doesn't sound that bad, but when you're getting down to this level of trying to really pinpoint where a star belongs in the HR diagram, that 50 degrees is a lot. You'd really like to get down to 10. So what you get out of the Bayesian method, of course, are probability distribution functions. You don't get single answers, and sometimes those are well behaved and sometimes they're not. So the ideal cases are the one I marked in blue, where you have a nice single peak, well defined, relatively small errors. Sometimes you get double peaked functions like green, but one's dominant. Again, not so bad. But then you have things like the red or the magenta or the orange, where you really have upper limits or lower limits or ill-determined ages. And the problem there is, depending on how you're applying this to a sample, is the net result for the sample is going to be biased, because you're going to tend to dwell on the ones you have good answers for, and you're not going to be able to understand the other ones very well. The composition's crucial. Got to worry about the color temperature relations, all this stuff. So this is the limits on isochrone ages. So let's talk about seismology. This is the great new hope, and it does offer an enormous amount of hope. There are still some very definite limits, and I'll point that out. So it's the newest method employed, by far the most promise. The idea is simple. You want to detect the equivalent of the solar 5-minute oscillations. The revelation of the oscillations of the sun, something Bob Noyes was instrumental in starting way back, was it allows you to see inside the sun. That's an absolutely breathtaking concept, that you can say things about the interior of a star by looking at its outside. And you can now say things in detail about the interior of the sun beyond what you could hardly imagine. And we can now actually do this for other stars. So on stars, you cannot resolve the surfaces the way you can for the sun, so what you detect are the very low order modes. But from the frequencies, you get the sound speed inside the star. From the sound speed, you get the interior densities. From the densities, you can infer the age. And you can actually get pretty good ages. It is model dependent, but that's okay. Everything is. Now, the problem is that detecting oscillations is even harder than detecting planets. I'll show you in a moment. Corot and Kepler are leading to big breakthroughs, but in radial velocities, you need to get below 1 meter per second, and in photometry, you need to get down to about the part per million level. Getting an age means you got to calculate detailed models for each star, generally speaking, and that requires good temperatures, luminosities, and a particular composition. So what does it mean? So the basic idea of the seismology is that we're talking about stars like the sun, which is to say they have convective envelopes. And those convective envelopes are hammering the convective radiative boundary constantly. And some of those frequencies that are set up by that hammering, just like in other situations, are resonant with the acoustical cavity of the sun. And you set up various modes in the sun or in a star, and some of those you can detect. In particular, in the stars, is that you can detect the low order modes. And when you look at there's two different kinds of oscillations. There's the pressure modes, the P modes that you see on the outside of the sun, and there's the G modes, which are deep down in the interior. Despite decades of effort, nobody has yet succeeded in detecting a G mode in the sun, which is a great shame, because it would allow you to actually probe the direct core of the sun and know its detailed physical properties and confirm that we really understand the core behavior of the sun. And this is certainly true for stars, but so you detect only the P modes in the outer part of the star. And so when you get a power spectrum, whether it be in radial velocities or in photometry, it looks something like this. And they have very characteristic patterns when they have good signal to noise like this. In this case, it's a solar power spectrum, but there are now stellar ones that look this good. You see a large frequency spacing, the large delta, which is the big frequency spacing of major peaks, and then there's a small frequency spacing, the small delta. And those two quantities are revealing of basic physical properties of the stars. And so you can, from the models, calculate a diagram like this, so-called Christensen-Dalsgaard diagram. And it relates to the mass of the star and the radius, and basically you can infer the hydrogen fraction in the core, which is essentially telling you the age. It's a lovely thing. If you go and look at velocity amplitudes to detect solar-like oscillations, you're getting down into the tens of centimeters per second. So it's a very difficult problem. It's been done on a few stars, but it's extremely difficult. So before Kepler, this was the situation. You could count them on one hand, literally. The stars that had asteroseismic ages. And obviously they're extremely bright stars. And the problem was not so much the signal as the very practicalities, that if you're going to measure these radial velocities, say, you're going to need a large telescope and a really good spectrograph. There's not that many telescopes and spectrographs to go around. You're going to need to do this for a series of observatories because you don't want to put up with the day-night diurnal cycle of, you want 24-hour coverage for the order of a week in order to do this. That's really hard to do. And then, of course, you have to pray to the rain gods once you get all those tacks to agree to even allow you to try this. And so it's an extremely difficult proposition. So it never got very far. I'll emphasize why this matters in a bit. Kepler changed everything. We now have seismology on dozens and even hundreds of stars. But I want to emphasize something. The diagram on the left shows all of the stars that Kepler has looked at for oscillations. The ones in red are the long cadence data at 30 minutes, and there you detect oscillations in the evolved stars, no problem. They're really easy to do. The dwarfs, on the other hand, you need 1 minute data because remember the sun has a 5-minute period, so you need to sample frequently enough to pick up that period. So on the left are the stars that have been looked at for oscillations. On the right are the stars where the oscillations have actually been detected. And notice the position of the sun there. On the left, I don't show the position of the sun, but let me tell you, they've looked at lots of stars where the sun is. You actually detect oscillations in very few of them. They have very low amplitudes. Now, this picture has been changing. They've been pushing harder on the data to work on the stars down near one solar mass. And so it's just filling in a little bit. But my essential point is the following. Even if you find a star, an interesting star, where you want to get physical information out of it through seismology, and even if you come up with the means to get those observations, that doesn't mean the star is going to cooperate and show you its oscillations. It doesn't work that way. Sometimes the amplitudes are just way too low. And in particular, getting down to one solar mass, it starts to get hard, and you get below one solar mass, and it just keeps getting harder. The amplitudes get lower and lower. So this is a very tough business. Now, in the Kepler era, there's been an effort to move away from the boutique analysis of the seismology into at least the retail level to deal with stars by the dozens, because they've got so many stars they just don't have the resources to analyze them in detail one at a time. So they've created pipelines, and this paper was an interesting one that looked at how well they could get results out for several different ways of analyzing the stars, because you've actually got different sets of models of stars, and believe it or not, even though all those stars are calibrated against the sun, because what else are you going to use, and you're using them on solar type stars, you don't always get the same answer for stars that are pretty much like the sun. However, the bottom set are the stars where they actually have spectroscopic abundances and gravities, which is a small subset. So they went in and tried to figure out what are the errors they're getting out on the quantities. And mostly, for most of the quantities, it's not too bad, but when you get to the age, it's pretty large errors. So if you don't know anything spectroscopically about the star, you get ages of about 34%, and this is from seismology, mind you. And if you have the spectra, this is through routine pipeline processing, is about 25%. These are systematic errors. If you do more detailed fitting with models customized to the star, you get down to about 10%, sometimes even better. I want to emphasize that even with the Kepler data, there's photometric noise. Here they talk about the noise in parts per thousand characterized from the Kepler data itself, and they point out that this presence of this noise, photometric noise, inhibits the detection of oscillations. So the gray points are all the stars they looked at. The black points are the ones where they detect oscillations, and you can see they're systematically down toward lower noise. There are some highish noise stars where they do detect oscillations, so it's not impossible. The red lines show you the range of variation you would anticipate for the sun itself. So sun, in that sense, is quite typical for these stars where they detect oscillations. So for seismology, the results are model dependent. That doesn't bother me at all. Everything's model dependent pretty much. Different models, different analysis routines can give you some significantly different answers, and sometimes this is up to 25%, even when you have good spectra to help you. The input physics can matter, like the equation of state, but when you have really good cases, like 16 sig that I talked about at lunch, you have just exquisite information, you can get the errors down to a few percent. It's just lovely stuff. And then I wanted to reemphasize here this important result that in some F stars with Kepler, they're seeing evidence of the core convection in the star. And as I emphasized earlier, this is telling us that we've finally gotten the physics of those stars right. And we're understanding the cluster age scale for young clusters. And I think that's a really good news. Okay, there's empirical age estimators, and you've heard about all these. There's rotation, activity, and lithium. I won't talk about lithium. That's only applicable to very young stars. Pre-main sequence down to about the zero-age main sequence. In these cases, you might have errors dominated by systematics because we don't understand the underlying physics at all. There's reasonable scenarios. We have our hand-waving arguments. What we do not have predictive power. Some indicators may work in some age mass ranges and not others. So the scenario. Solar-type stars go through several changes as they get older. They spin down and they decline in activity and they lose lithium. So you know the explanation. You've got rotation, and a particular differential rotation. It interacts with the convective envelope and gives you complex motions in a conducting fluid, and that gives you a magnetic dynamo. If you've got a seed field, you're generating magnetic fields. You take that magnetic field, you've got an ionized wind like we see on the sun. That means that field can grasp the wind out beyond the surface of the star, put angular momentum in it, the star spins down. Those magnetic fields are manifested as H and K lines, for example, as activity in stars, H alpha, X-rays, and things like that. And all of this is based on what we see on the sun, and it all fits in qualitatively with what we see in stars, for example, in clusters. And this mechanism includes feedback, beautiful thing, so that rotation rates converge over time. So if stars start out with high rotation, they generate stronger fields, so they lose angular momentum faster, so they come down and converge on a time scale of the order of 1 billion years. So it's easy enough to see this observationally. The top cluster, NGC 2264, is pre-main sequence. It's basically T-Tauri stars. And you see a spread there of the order of a factor of 50. That spread has maintained itself all the way down to the zero-age main sequence at M50. It's not hugely different. By M34, another factor of 2 in age. Now you're seeing a lessening of the overall scatter, and it's a little bit better behavior. And by the time you get to the Hyades, not so well represented here, essentially the spread has gone away for the higher mass stars, and that's the convergence I was talking about. So there's been an effort to calibrate this so-called gyrochronology by Barnes. And this is the same thing, looking at it in a different axis. So you've got age and the rotation rates, and of course there's a broad range of masses at any one of these ages. We do not understand this very well. So the idea is that gyrochronology uses the sun as the anchor for old stars. There's so far been no improvement on this because we don't have anchor points for the old stars. And it assumes the t to the minus a half law of Kinematic. We have the potential to improve this with Kepler. By getting seismic ages and then applying other information. And then we really don't know what's going on at lower masses than about 0.8 of a solar mass, maybe the middle Ks. And it's not useful above about 1.2. They don't change very much and they have short main sequence lifetimes. So rotation in terms of V sin I or even the period, it can be difficult to detect in older stars. It's a practical problem. You might have biases in your ensemble. Even when you look at a cluster, you only see rotation in about half the stars at any given time because the rest don't have enough contrast in the spots to show you a signal. We have no idea what happens with metal poor stars. There's noise from differential rotation, which is also something to study, of course. And there might be biases, because if you have close-in planets, there could be effects. Or you might have merged planets, and the star is rotating faster than it ought to by rights as a single old star. There's empirical ages from activity, which is basically a related to rotation. I want to say spin-off. That wasn't quite what I meant. But so the classic thing, this is a star very much like the sun, and those little itty-bitty blips down there in the bottom of the calcium K line down in the ultraviolet, those are the chromospheric emission features, and believe it or not, those are actually not that hard to measure. You can use low-resolution spectra. Low to me means an R of about 4,000. So, and getting R of 4,000 on stars in the near part of the galaxy is really not very hard anymore. So it's actually quite easy to measure. The problem is does it actually do any good? The chromospheric activity has a lot of things going on with it. You've got random variations. You might have flaring or other short-term effects. You've got rotation, of course, so you've got spots going around, and that modulates the chromospheric emission as well. And then you have long-term cycles, like the solar 11-year cycle. So you've got a bunch of things working against you. You can come up with a very nice age activity calibration, which is what I did here a long time ago. And the reason it looks so nice is that I've averaged out all the noise. And all those points are for different clusters and groups of stars. And it's the averaging that kills you, because in reality it looks more like this. And even when you get into an old cluster like M67, those triangles down near the bottom, that's a cluster that's essentially the same age and metallicity as the sun, about 4 billion years, and the stars are not that well behaved. So that's not very reassuring. And then you can also go out and look at stars in binaries, and you would hope that the two stars in binaries pretty much agree in their activity levels, and they kind of sort of do, but then there's notable exceptions. So again, not very reassuring. And then there's been suggestions, in fact, that activity just totally flattens out after about 2 billion years. I think that remains to be seen. We really don't know. And then there's statistical, which I would say are largely fairly useless or misleading. And the reason I say that is there's a fairly well-known and established age-metallicity relation, but it has huge scatter. And in part, that age-metallicity relation is as likely to be an artifact of radial migration in the galaxy, and the fact that we have a mixture of stars of initial abundances in the solar neighborhood as opposed to there being an innate age-metallicity relation. And then there's the one with kinematics and age as well, which you can maybe apply to groups of stars. So the perfect age indicator, you can measure it, it's sensitive, large variations, you can calibrate it, you understand the physics and so on. How well do these things do? So you only got a fundamental age for the sun. That's from solar system material, not from the sun itself, I do emphasize. I'm sorry for going over. I usually don't do this. I apologize. Oh, you're right. I'm not. Thank you. Good. Got left time for questions. I was trying to. Semi-fundamental ages, boy, they really ought to work, and they just don't. Kinematic, only for very young groups at best. Isochrone placement. Okay, it's cheap. It's really cheap because you can do it on lots of stars. You need to get some spectra. Okay, that's not that hard. It is vulnerable to transformation errors, particularly temperature problems, so there's some systematics. You can't get down near the zero-age main sequence. There's just too much degeneracy, so that limits you and applies some biases. You need some careful analysis using Bayesian methods, so maybe it's not for everybody. You need to know what you're doing. But it is based on modest extension of solar models, so it should be reasonably reliable within the context of those models. We have not tested those so much for low-mass stars. There's a limitation. You don't get a firm age back. You get a probability distribution function, but that's okay. And it works best for higher mass stars. Seismology, enormously expensive. What I was trying to say earlier is that Kepler has revolutionized seismology by its simple virtue that it exists. Now, I'll let you think about that for a second. You can't just go take Kepler and point it at something that's of interest to you. First of all, they won't let you. And second of all, by the time you want it, it isn't going to be there. So, you know, that it isn't an asset that exists is the point I'm trying to make. So there are stars of interest to you, and if you're interested in that star, you can go get time at a ground-based telescope, you can get a nice spectrum of it, do all kinds of things. But because you want to get seismology on some star of interest to you, doesn't mean you're going to get the data on that star that you want. Now, Dave's looking at me here, and it is fair to point out, TESS will solve some of this to a limited degree by doing pretty much an all-sky survey of a lot of stars. And K2 may help too by doing a lot of stars along the ecliptic. But my essential point remains that even though in principle you can get seismology and a lot of information for a star, that's a completely different matter than having the means at hand available to get that information. Not all those stars even show you their oscillations after you put in all that work to get it. The nice thing about Kepler, of course, is its multiplexing advantage. Based on modest extensions of solar models, that's good. We have not tested this on low metal stars. You need good estimates of temperature, gravity, metallicity, but it's well suited to older stars, and it may well work for evolved stars too, and it may be a good stepping stone for the empirical indicators. Rotation could be very cheap. You can get the rotational signal easily sometimes. The periods are the order of 1 to 6 weeks, so you need a lot of data. Not calibrated on stars that are not like the sun. There's some inherent biases and uncertainties. Activity, in some ways even worse, because it's secondary under the rotation. It's basically driven by the rotation. So you have added uncertainties. All I was doing here was re-emphasizing that the lithium depletion boundary ages in the Kepler seismology support the so-called new cluster age scale. It's not that new, which increases ages by up to 50%. So that's very reassuring. So we want to go industrial. So if you want to approach galactic problems, you really want ages for a whole bunch of stars. Right now we do it on a boutique basis. We can get the uncertainties down to 10%, sometimes better. We can go to retail, meaning dozens of stars, and we have to throw away precision to do that. But sometimes you want to get up to the 100,000 star level, and how can we do that? So you've got to be able to use readily obtained quantities, and that means photometry or maybe moderate resolution spectra. That can mean maybe calibrating the age-rotation relationship or activity, or maybe using isochrones. Rotation versus age is probably less noisy than the activity. We can use the stars with seismic ages to calibrate other stars. The nice thing is, for highly evolved stars, the seismic amplitudes get to be really large. If you get up to the asymptotic giant branch, they reach the millimagnitude level, so they're really right at that edge where you can start to do it from the ground. And from the oscillations of an evolved star, you get the mass. If you know the mass, you know the age. So you're pretty much done, and you can see them all the way across the galaxy. So those offer very nice hopes. So what are my hopes? The high precision photometry of Crow and Kepler can give us enough good ages so we can go out and test other things. Maybe one of these days we'll actually understand the solar dynamo, and that means we can turn what we call the empirical ages into model-dependent ones, and that would be nice. Kepler was now going to turn into K2. I did not think my life could get any better than Kepler, because here I have dumped on me the mission of a lifetime that looks at 100,000 solar-type stars beautifully for 4 years on end. How can life get any better? K2. It's a beautiful thing. It's going to go survey the ecliptic orbit of Kepler. And the reason it's technical, because in the ecliptic, given various technical constraints, you can maintain the pointing pretty much near as well as the original mission. And that means the photometry is pretty much near as good as the original mission. But in the ecliptic, the original Kepler field is about 15 degrees out of the plane of the galaxy. And that was chosen very carefully to avoid young stars, because young stars are photometrically noisy, and you're not going to find planets around the young stars. So they chose a field full of old stars. And you can demonstrate that because there's 3 or 4 clusters in the Kepler field, and the youngest one is 500 million years old. And that's old for a cluster. So there's no young stars in the Kepler field. But by going around the ecliptic, we get to hit the Pleiades. Oh, man. The Hyades, M67, M35, Praesepe, the list goes on. It's going to be a beautiful thing, including some star-forming regions. So we get to apply the capabilities of Kepler to a whole new host of stellar problems. It's a really exquisite thing, just in case you couldn't tell. We can hope to improve agreement among stellar models. And here I mentioned CNO abundances, and I was talking to Bob Cruz earlier, and I think he might have an answer for this in increasing opacities inside stars so we can live with the aspirant abundances and the conventional solar models and get the frequencies to agree and everything. So that would be nice. Someday, at a recent talk, somebody asked me, well, you know, in principle, is there any way you could really get the age of a star? And I said at the time I didn't think there was, but I realized later I was wrong. If you could ever hope to detect G-modes in stars, those probe the very core of the star. If you could ever do that, you would really nail the age. That would be really unambiguous. And then finally, we can hope that one of these days we're going to find that planet with the biomarker and establish its host age and gain a new insight into the story of life. And so I will close by mentioning that last year was the centenary of the invention of photoelectric photometry, that Paul Guttnick in Berlin in 1913 made the first photoelectric photometer. At the same time, I will say Joel Stebbins in Illinois also developed one. So they were going on at the same time. And that's all. And if and the only other thing to say is I did try to leave time for questions, because if you don't have questions, you were not listening. There was lots of things to ask questions about.
Yes, I will mention that Plato, or some of us call it Plato, was selected yesterday,
yes,
and is basically an astroseismic mission,
yeah,
to launch in 2024.
Yeah.
Yes, 2024. You'll make it. Okay, we'll go around. Dimitar?
So, speaking of hopes for the future, Dave, what about any new ways to get ages for M dwarfs? Fuel.
Guilt by association.
Yes.
Probably is the best hope I can offer. You associate the M dwarf with some other object. In and of themselves, they're intrinsic properties. I don't see a way, but on the other hand, we know so precious little about them. You know, they're not really very well characterized because they've always been so faint and difficult to work on in detail. And also the atmospheres haven't been well understood. You know, there's been lots of impediments. So it's reasonable to think that we could start to understand M stars a lot better. And we're starting to get to that point where we now have decent atmospheres for them, for instance. That's pretty amazing, actually.
Yeah, Trent? Oh, Jeff. All right, I'll get to you, Trent.
Okay, so you said at the end, well, it'd be great to detect the G-modes.
Yeah.
But we haven't even detected for the
Exactly,
sun.
yeah.
Can you just tell me what's the obstacle? What is the status of detecting G-modes in the sun?
I'm not really the right person to answer this, but the simple answer is that they're way down. They're buried so far down in there that there's no signal left at the surface.
And maybe other stars would give their
I'm
G-modes up.
I'm not offering any hopes at all.
Okay.
All I'm saying is if you could detect them, they probe the core. That's all. So in principle, I mean, look, there's lots of things we detect these days that 30 years ago seemed beyond conception, right? So I do not deny the possibility of anything.
Mermaids.
Looks like we're stuck in the front row here.
Suppose you could get the G-mode, you said, then you could really
because it gives you the central density.
Yeah.
And so that tells you how much of the hydrogen's been converted into helium. And I think we understand that part. I'm pretty sure. I know nothing more fundamental related to age of the star than the core of the star. Right? Everything else is model dependent in some way or another.
All right, we're going to the third row.
Yeah.
Trent?
Okay, so in a couple of the recent Kepler astroseismology papers, they actually plot the astroseismic ages versus rotation period and calcium HK. And I was shocked when I looked at these that they're saying stars that are rotating relatively rapidly, several days or something, that I would think would be sort of Hyades age, maybe a little older. They're putting it at like the age of the sun. Systematically, all those stars in that group would be at the age of the sun. And the sun is this huge outlier on their plots. And so I was wondering what's going on with this. Because you talked about random errors, I was thinking.
Those are not random. And I don't have an answer for you. I haven't seen it, so I got to take a look at that and think about it. But I agree, it doesn't look. Yeah.
I was just wondering for the activity, age activity indicators. When they're considering those, do they consider the intrinsic variability of the line at all, or is it just a snapshot?
So typically, you're getting a snapshot. I will say the following. I did this in a paper eons ago from the Mount Wilson survey. Mount Wilson people surveyed H and K emission in the solar neighborhood. So you knew the H and K emission for a bunch of stars, a couple hundred G-dwarfs out to about 20 parsecs. And for many of these stars, you had not just snapshot data from the survey, but you had very long-term observations as well because they were looking for long-term cycles. So you could say, if I just had the 1 or 2 observations, how well does that agree with the long-term average? And the answer is actually extremely good. It was about 8.08 dex, something like that. So 20%. So if you take a single observation, you're typically within 20% of the long-term average. Which, if you think about it, for sinusoidal, quasi-sinusoidal variations is not a big surprise. That's kind of how things behave.
Yes.
So, given the finite amount of data that we have with the Kepler field, what do you think can we realistically expect in terms of getting astroseismic ages when we go down the stellar mass vector, basically? How far down can we go? Do you think early K, mid K?
I think it's going to have to be done with radial velocities because the photometric amplitudes are too low, but the velocities are more amenable. But it's observationally, of course, it's incredibly demanding. Now, what is being tried is the Europeans are the people doing this stuff. They're really at the core of CASC, the Kepler Asteroseismic Science
Soon to be
Consortium.
task, by the way. The K goes to T.
Okay.
You know what T stands for, right?
What does it stand for?
Test.
Yes. So, but anyway, I mean, they have this huge effort going, right? And the Danes in particular, where they have the Asteroseismology Center in Orbs, they want to build a network of radial velocity devices to span the globe so you can get continuous coverage of radial velocity, SONG, that's it, Stellar Oscillations Network Group, to be able to follow stars from the ground to do the radial velocity work. And you're not going to do huge numbers of stars, but you can get the kind of data where you can start getting, really good insights. So for example, 61 sig, not 16 sig, but 61 sig A and B, or K5 and K7. So that's getting far enough down in mass, they're starting to get really interesting. They should be distinctly different than the sun. Wouldn't you like to know what's going on there? So those would be, and they're really bright. So those are the kinds of things you could imagine doing and having a lot of fun with. There's still a lot of things left to do.
Should we move to the other side of the room? Do we have anybody doing gyrochronology over here? Tell us about the Kepler results.
Well, I mean, in favor of using rotation, we are, as you know, capable of defining how stars rotate with other masses than the sun to clusters with model-dependent but rather well-determined ages, up to 2.5 gigayears.
Nothing wrong with model-dependent, that's cool.
So, and it fills a fair number of those things we like to think about as good age indicators. Rotation. So while it's not perfect, there is progress using the clusters in the Kepler field.
It's a completely fair, accurate, and complete statement. Right, this is what we're here for, is to fill in the gaps. And so this is what's going on. So right now we don't know very much about the old stars, but we're getting there.
Yeah, and we're pushing it to early mid-K, so below the sun. So there's some hope in this empirical. We don't understand the physics of it. So.
And all of this is of a whole, because when you go look at these clusters, the older ones tend to be distant, and the stars are really faint, and the membership knowledge is terrible. And especially when you get down into caves, they all look like everything else.
That's the story of his life.
Yeah.
Determining the membership so he can do this science.
Man, it's really hard work.
Charles?
I don't know why two Daves are in such a good mood, because this talk's left me really depressed.
So I pretend to offer no solace,
No, there's more fun to be had, Charles.
After all this time. But can you always reliably tell age order whenever it matters?
No. And here, I'll give you a concrete instance where it really matters, and that's in pre-made sequence stars, when you're trying to determine the age scatter in, say, a group of T-taurus. And you'd like to know what the age ordering is, and you really have a hard time telling because there's a lot of unknowns. The accretion history, for example, can very definitely influence the HR diagram position of one of those stars and make it look like a different age than it might really be. So even there, sorry.
Well, I mean, again, when you get to beyond a few 100 million years, rotation
It's,
is a fairly consistent.
yeah, it looks that way. We have a lot of calibrating to do, but it looks pretty reasonable.
But not in the young, for very young stars, you have a large dispersion.
Yeah,
That is not well understood why some stars are fast and slow at the same mass and the same age.
Yeah.
But once you get beyond the age of the Hyades, for example, it becomes a fairly continuous decrease.
See, this doesn't depress me because some people think scientists are in the answer business, and I say, no, we're in the question business. And so I always end up with lots of new questions to work on, and I'm happy.
It's been going on for a while. Cosmology's kind of got there, right?
Sometimes.
That's only a limit.
I'm naive. I thought the radioactive decay rates were reliable. I mean, ages were reliable. So what's going on? Why aren't those working?
I think that the fundamental limitation is just observational because you have basically a very few spectrum features to work on. You're making this assumption, of course, about scaling our process elements to get the initial abundance of your thorium, and you can see from the other our process elements, you don't get the same answer all the time. So there's an obvious limit there in our knowledge of actually the creation of our process elements. So conceptually it's reliable, but there's missing pieces we don't understand. And observationally, it's a tough business. Very faint stars.
Anybody in a peanut gallery?
Yeah.
You said the sun you can measure to 4.567
Yeah.
accurate to 1 million.
Yeah.
Come from what? From what exact point?
It comes from measuring meteoritic material in the laboratory. old meteorites, carbonaceous chondrites and the like. Yeah.
It's not
the sun tells you nothing about its age, not itself. No star does.
So it's the age from when the material was first solid?
That's right, and that's where you get the systematic error because you don't know precisely the ordering of events in the early solar system and so on.
Soren?
So there was, in this plot you showed with the stars of which there were astroseismic ages, there was a curious little clump of stars slightly cooler than the sun. Is there anything to be said about that?
I wish I knew the answer to that, why those stars worked.
Like a cluster of 7 or 8 stars.
I saw
at the
that,
same time.
and I don't know the answer to that. Yeah, interesting, isn't it?
Yeah.
But stuff happens.
I think you just have to ask Hans Jørgensen and he'll have the answer.
It could be that somebody decided to really beat on some particular color range or magnitude range, and it could be, in other words, what I'm saying, anthropomorphic or something like that.
Well, could you comment about solar twins?
Yeah.
For example, solar twins in clusters could be useful.
Yes.
This kind of calibration. So,
how do you establish that they're twin?
well, stars very similar to the sun. I mean, very proxy. Some proxies like 80 Scorpion.
So my concern is that if I want to establish that a star is like the sun, I would really like to know the mass and the age, and then look at all the other properties and compare those properties to the sun. Not start by comparing the other properties, because that seems to me to lead to circular reasoning.
Yeah, well, I concern so solar twins in clusters. Maybe this can be different.
Yeah. Now, unfortunately, nature put M67 just far enough away to be real.
875. Jessica?
Is it possible that getting higher signal to noise spectra from bigger telescopes is going to help with measuring the radioactive element?
It certainly gives you a much greater reach. There's no question about that, because it's been so limiting. All of those really low metal stars are really faint, and so there's no question that people like Chris Needham and his disciples will be hitting more of those stars once we get larger telescopes, and you can get those good spectra. So I'm sure when we see more results, and maybe it'll give us some additional insights that will get us somewhere.
That's one of the science cases for G. Cliff on the GMT.
Yeah, thank you.
Right, Andy? Well, we're at 5 o'clock.
Almost.
Thank you very much.